the screen of mathematics. To the screen of mathematics. All right. Slideshow from current slide. So what we did last time was looking at monotonicity, extrema, and also the greatest and the least value of a function on some certain segment of x values. So for a quick revision, some exercises, and then we will move on to the next topic. And so, all right, looks like I need to get my white pen. Okay, so let's remember that the first derivative, positive at some point, means the slope of the graph is positive at that point and the function is increasing. The first derivative, negative at some point, means the slope is negative and the function is decreasing. The slope of the tangent line, the slope of the graph, negative means the function is decreasing. The first derivative equal to 0 at some point, it means that the slope is horizontal, that the tangent line is horizontal, and it's at these points that we could have minimum points, maximum points, or sometimes neither minimum nor maximum. We call these stationary points because the function seems to be standing still at that one single point, but a stationary point could be a maximum point, could be a minimum point, and could be what we said an inflection point because it's not minimum, not maximum. We will consider more about these inflection points later today. And then, of course, there's one more possibility. It is possible that at some points, the first derivative is simply not defined. At that point, if the value of the derivative, if the limit of the derivative tends to infinity, we might think the tangent line to the graph is actually vertical. In that case, it was possible to have a spiky kind of minimum or maximum, something like, for example, this, something that we had last time. Something similar to this. It's possible to have. It's possible to have. And so, after this very quick reminder about how we determine, how we detect these things, let's investigate this function because it has an exponential factor in it. That means it's not a polynomial. Perhaps determining the sign of the derivative in different segments might seem difficult to you, although it's actually not. So the derivative of this function is, it's a product. So x differentiated 1 times e to the power x plus 1 without differentiation plus x without differentiation times e to the power 1 derivative is e to the power x plus 1 is e to the power x plus 1 times derivative of this exponent, which is, of course, 1. I am writing it down simply to remind you, because I know that people tend to, let's say, ignore some things. E to the power x plus 1. And now we see from this we only have 1 from the first factor, from the first term, and from the second one we have x. And now, what we see about the signs, I know that e to the power x plus 1 is always positive for all x values. It's never 0, never negative. So basically, the sign of the derivative is determined only by this second factor, 1 plus x. So that's the only moment where we can get a critical point. So if the derivative is 0, if and only if 1 plus x is 0, that is if x is negative 1. So the first factor, e to the power x plus 1, does not influence the sign. It's always positive. So all we have to do for the sign diagram, and now please remember, it's a sign diagram is required. I have had some people complaining that we study from blah, 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 whatever. So, dear people, if you study from blah, 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 whatever, and not my lectures, then you have to tell me when you are writing the test or examination, where did you got that I haven't taught and what it means and what you are doing really. Because otherwise, sorry, I cannot trust your work. And this is something that those people tend to omit. The sign diagram, that's experience talking from previous semesters. So I absolutely require sign diagram to investigate monotonicity and to investigate the second derivative as well in the upcoming topic. So this is a warning. Without sign derivative, I will not accept your answer. Because otherwise you have to write 3 sentences to explain why and how you got the answer. Sign diagram is the quick and easy way to show where the answer comes from. So when x is minus 1, the derivative, the first derivative, is evidently 0. But if x is greater than minus 1, then evidently we can see 1 plus something greater than minus 1. You may choose any point you like that is greater than minus 1. So this 1 plus x factor will be evidently positive for larger x values, and for smaller x values, the derivative will be negative. And the second part of the sign diagram, we have to determine the behavior of the function. We see for x values less than minus 1, the function is decreasing because the derivative is negative. And after minus 1, the function is increasing because the derivative is positive, which means at minus 1, we have the minimum point. So minimum at minus 1, and now we have to determine the function value at this point, minus 1. Minus 1 e to power minus 1 plus 1, minus 1 times e to power 0. We know that e to power 0 is 1. So this is also minus 1. This is the minimum point. Minus 1, minus 1. X and y values are both minimum point, minimum values. Sorry, minus 1 is the minimum point, and minus 1 is the minimum value of this function. And for all the other x values, the derivative is not equal to 0. We see that it starts by decreasing to this point and then it increases. The one thing that is not very, very clear, perhaps, the one thing that might not be very clear is that the shape of the graph as such. The shape of the graph as such. The shape of the graph, well, is not obvious from this. It could be something parabola shaped. It could be something, again, shaped somewhat differently, like, who knows, like this, with a curving back in a way, while still increasing, the slope might change to something different, something much, much slower again. So we don't know yet. Today, a little bit later, we will see.
Miss, so do we need to draw a graph?
At this point, no.
Okay.
At this point, no. If your task, well, basically, in the homework, yes. In the homework, yes. Because you will do the full investigation for the home task. But for this, for the class test, for instance, the task will be exactly this. Determine the segments where the function increases, decreases. Determine minimum, maximum points, things like that. This is not requiring a full graph because this is not enough information. This is not enough information, but for the homework, you will get full information about the function. So in the homework, yes, but in the test, no.
Okay.
Okay. Now, next. We had a look at this. We had this derivative that actually consisted of 2 parts, and the graph looked as a result something, well, not exactly this, but the idea was the minimum point was the spiky kind, because at x is 0, the derivative is not defined. And then there was, I think, the point, was it 8? Maybe. Yes, it was 8, I think. At that point, we had the regular stationary point, which turned out to be the maximum point. So the conclusion is that it should look something like this. We don't know about the rest, what the rest of the graph looks like. So the reminder for you was that when you differentiate this function, you should simplify the derivative to the most, let's say, efficient form that was including the radicals and including, let's say, excluding negative exponents. So in principle, the derivative is found in two pieces because there are two terms. But if you remember what we did last time at the end of the lecture, or close to the end of the lecture, was that we saw that it's best to bring these two terms on the same line, on the same common denominator, and using radicals, using roots. And that means that only then we can get full information from that derivative, because otherwise, if you simply write the derivative um, 2/3, that would be 2x to the power minus 1/3 minus 1. If you write the derivative like this, you might be able to find the x value for which the derivative is 0, but you lose, definitely, you lose the point where the derivative is not defined. So the situation was that we had to find the denominator, the common denominator is cube root of x, because this means divide by cube root of x, x to the power minus 1/3, 2 divided by cube root of x, as this first term, minus, and to put 1 on the same denominator, we have to write cube root of x, which meant that the derivative is not defined if x is 0. Therefore, we have this vertical tangent line. And if x is 8, then the derivative was equal to 0, which means the horizontal tangent line, actually the stationary point. And then we could look at the signs. We saw that if x is large, then we have a negative derivative. If x is negative, we have again negative derivative. And if x is between 0 and 8, we saw that we could get a positive derivative, which is how we concluded, which is how we made this conclusion. I am not writing the sign diagram at the moment here. Well, I can actually. So this was the derivative of the function. We must simplify it to this form. Then we see that the two critical points are 0, where the function derivative is not defined, and 8, at which this derivative is 0. That's why I am doing this notation. That's why I'm doing these notes. And then we saw if x is very large, positive, this becomes negative. So the quotient is negative. If x is between 0 and 8, you remember, you may check any point for the method of intervals, any point between. So a good point would be 1, because it makes a good cube root. 2 minus 1, positive, divided by 1, positive. And if x is negative, then we see that the cube root of x is negative. However, the numerator would be positive, and the quotient would be negative again. So we see this, and the interesting thing was that if x is 0, the function value exists, because you can put in 0 into the function and see function at 0 is 0. It exists. Only the derivative does not exist. And the second point, 8, we see, so we have a minimum, but it turns out to be this spiky kind, although it's not a mathematical term. When I say spiky, it's like I'm just describing, showing you what happens there. It's only a description. It's not a definition. It's not a mathematical term. It's only to describe what it looks like. So it's not a mathematical description, not a mathematical term. And when x is 0, we see we have a maximum point. Sorry, not 0, but 8. So 8 squared is 64. Cube root of 64 was 4. 3 times 4, 12. 12 minus 8 is 4. And the thing is, I have sketched a bit incorrectly because the function has to be only decreasing on the left of 0. It cannot be this. So this part is not accurate. Well, I can say that this altogether is not very accurate. The illustration, let's say the part that can be considered correct and accurate, is this part to illustrate this situation, and this part, which is to illustrate this other situation at the point 8. So that's important. There are two kinds, as we say, two kinds of extremum points, like the stationary points and the other critical points, which need, of course, to be investigated separately. Now, I think we did not do this. We only had time for one example last time for finding the greatest and least values. Finding the greatest and least values on a segment. So not the total greatest value, not the total least value, not all of them exist in fact, but on a certain segment. So to write, we start with the derivative, of course, because we start by finding, remember, we have to start by finding the critical points, the points where this greatest and least value is possible, because they might be minimum maximum points. So 24x squared minus 12x cubed, and that's it. That's the derivative. This means that we have 12x squared out of parentheses, and then we might write 2 minus x. So factorize. This is the moment, as I already mentioned last time, where we need to factorize the derivative, because without that, we cannot investigate the function. We need to see where the derivative is 0. And we see there are 2 points. So one critical point is x is 0, and the other one, as we see, x is 2 critical points. And the derivative exists everywhere. No critical points of the second kind. So these are stationary points only. And the other critical points don't exist because the derivative, evidently, it is defined for all values of x. Now, the difference from finding monotonicity, finding extremum points, we don't have to investigate which one is the maximum point, which is the minimum point, and so on. We only need the values. In this task, the question is about the values of a function. And I would also like to remind you that the greatest and least value of a function may happen at a critical point inside the segment, but it might also happen at some point on at one of the endpoints of that segment. And therefore, we consider, so the critical points 0 and 2, the segment of interest is from -1 to 3, actually. So in this case, what we need to do is we need to investigate the function values at all 4 points. I am not determining signs. I am not drawing any arrows. I'm not investigating function increase, decrease, because regardless of if 0 point, for example, if the 0 point is a maximum point, it doesn't tell me anything, because at one of the endpoints, the function value could be even greater. And therefore, I do not bother determining extremum points, minimum, maximum points. I simply find the values of the function. So function value when x is -1, we have 8 times -1 minus 3 times +1 plus 1, so this is -10. Function value at 0 is evidently put in 0, 0, that's 1. Function value at 2 is 8 times 2 cubed 8 minus 3 times 2 to the 4th power is 16 plus 1, so 64 minus 48 is 16, plus 1 is 17. No, wait, something wrong.
Ma'am,
What? Yeah.
why can't we use second derivative to find the greatest, or and like finding the minimum and maximum? We could use.
We will do that when we deal with second derivative later today. They can be used. However, in this case, it won't work because no matter what the maximum minimum point is, it is quite possible that we actually have a greater value at the end of the segment C maximum, but perhaps at the end point of the segment, the function is greater. In this case, it will not work.
Okay, okay,
In this particular situation, it's not helpful. It's not helpful.
okay.
Right. So we see that we have 17, and then we see at the end point at 3, we have 8 times 27 minus 3 times 81 plus 1. So that would be, okay, I can 8 times 27 minus 9 times 27. I simply rearrange this product a little bit so that I can say, okay, this is minus 1 times 27 minus 27 plus 1 is minus 26. And now we see very clearly that this is the greatest. So this is the greatest, and this evidently is the least. So the answer would be greatest is the function value at 2. That is indeed at a maximum point, and that's 17. And the least function value is at 3, where the function is actually negative 26. So we see that, yes, what we see with this situation is that y is 0, nothing. So we see that x squared means that when we pass through 0, the derivative will not change the sign. For very, very small positive or negative x values, x squared will be positive. So the sign simply doesn't change when we are passing through 0. And basically what happens at 0, because we might think, okay, it's smaller, this is 1, then we might expect it going down again from this critical point, from this stationary point, but it does not go down again. See, we start the smallest value, small value minus 10, then at 0, we reach the function value 1, and then the function value goes on increasing until it reaches, at 2, it reaches 17. And only then it goes down and reaches minus 26 at the second end of the segment. So sometimes, well, this is not required. This is not required. This was only an illustration, a general illustration, this part. So this is not required for this task, and this is also not required. It's only for those who, let's say, understand how these values can be used to understand what the function does, how the function behaves. It's again not required, not required. At this stage, we do not require any graphing, only determining the values. And so we see that if we only consider x from this segment, from -1 to 3, then on this segment, the greatest value is 17, that's at x is 2, and the least value is at 3, the right end point of the segment, and the smallest, the least value is minus 26 for this function on this segment. Of course, it's quite possible that one of the critical points that you find from the derivative is simply outside that segment. Please remember that in that case, we ignore that point. We are only interested in the points of that segment. Another one. So the derivative, please, okay, first of all, please remember that the function is 8 times x to power minus 1 plus 1/8 times x. So x divided by 8. Don't use quotient rule. It's messy, clumsy, and useless. Imagine, think in terms 1/8 times x. It's a constant 1/8 multiplied by x. And so we can write the derivative. This will be minus 8 over x squared plus simply 1/8. And again, to understand, to see the critical points, we have to pull these two terms together on the same line, on the same denominator. So the common denominator is 8x squared. Then we have minus, so we have multiplied by 8 minus 64. Here we multiply by x squared. So that's plus x squared. So we see x squared minus 64 divided by 8x squared. We see that if x is 0, the derivative does not exist. But looking back at the function, actually x cannot be 0. The domain of this function does not allow 0. So if x is 0, this function is not defined. Not only the derivative, but in this case also the function itself. So now we have to understand what is going on. Even here, x is not 0, by no means, because of this, first of all. And then we say the derivative, the critical points, the derivative is 0 if x is positive or negative 8, as you can see. And so we have one critical point, negative 8, one critical point, 8, positive 8. Then x is actually not equal to 0. So basically, there is a discontinuity. This function is not continuous in real numbers. We see that when x is 0, we have this type 2 discontinuity, because when x is 0, the function goes to 0. The function itself tends to 0. And now at this point we don't need the derivatives. Sorry, I was just, without thinking, I was doing this mechanically. The segment is from 4 to 12. All right, let's mark from 4. So this was 0, from 4 to 12. This is the segment of interest. This is the segment which we actually want to consider. Fortunately, 0 is outside that segment, because if we have an interruption point in the segment, then this method doesn't work. This whole idea is absurd, because then inside the segment we reach infinity. So we cannot really find the greatest or least value. So we have to make sure that, of course, this is only possible, finding the greatest and least values is only possible if there's no discontinuity, if the function is continuous on that segment. So we see that, yes, there is a discontinuity outside the function. The domain does not contain the number 0. Fortunately, it is outside our segment. Otherwise, we would have, I would say, trouble. And so now we simply find the function values. Function at 4, function at 8, and function at 12. If x is 4, we could say 8 divided by 4 plus 4 divided by 8, that's 2.5. If x is 8, we have 8 over 8 plus 8 over 8. This is 2. And if x is 12, 8 over 12 plus 12 over 8, that is 2/3 plus 3/2. This is something over 6. 4 plus 9 is 13. So we have 2 and 1/6. I had to change the form in order to see. Now we see that 2.5 is of course greater than 2 and 1/6. So this will be the greatest. And 2 evidently, just 2 is evidently the least value. So the greatest function value is at 4, and that is 2.5. And the least function value is at 12, that is on this segment, of course. Sorry, at 8. At 8, and their value is 2. So the difference is little. That's not much difference between 2.5 and 2, but well, we have to consider the scale of this graph and the way this graph actually looks like. But that's something that we can determine later on. Definitely not today yet, but hopefully next time on Monday, we'll be able to investigate this function more fully. Okay, another function that is rather unpleasant, that's the last one, I think. I think it is the last one. No, yes. Oh, okay. And yes, then we have a new topic. We move on. All right. So in this case, the derivative, okay, the square root, this might become somewhat messy. So let's have a look at this derivative. We see that this derivative, the function actually, the domain of the function is actually only for x greater than 1. X cannot be 1 because we cannot divide by 0. X cannot be less than 1 because then we will have the expression inside the radical negative. If x is less than 0, then this bottom part, the denominator, is negative. You cannot find the square root of a negative number. So the domain is only x values greater than 1. This is useful so that we don't worry about anything else. And so now the derivative to find the critical points. The derivative, well, now this will be chain rule. The derivative, actually, if x is greater than 1, then x is positive. In fact, I can then rewrite this function. First of all, if x is greater than 1, then I can take square root of x squared. Square root of x squared is simply x, because it's positive. X is positive, and the root is, of course, the main root, also positive. Square root of x minus 1. So now we can use simply the quotient rule. Now we don't have to use the chain rule. Square root of an expression would imply the need for chain rule. However, we can sometimes simplify the function, so we don't need the chain rule, but only the quotient rule. So uv. So v square means x minus 1 without the square root for the quotient rule. Now x derivative is 1 times the denominator v without derivative minus x without derivative times denominator, this small square root differentiated. That is 1 divided by the 2 such square roots. We should also multiply by the derivative of x minus 1. But okay, it's 1, so nothing changes really. So in this now, to simplify it further, because to investigate the function, to find the critical points, we do need to factorize everything. So this is the moment where let's multiply the numerator and denominator by the square root of x, which means we have x minus 1 times square root of not x, but x minus 1. Here, if I multiply by square root of x minus 1, multiplying this by itself will give us x minus 1, as you well know. Multiplying this, we get x over 2. You can see it's x divided by 2 because these square roots cancel out. So if you like, you can actually also multiply by 2, but this is not strictly necessary. So we see that the derivative is 0 if x minus 1 minus x half is 0, because the denominator is always positive from domain. Looking at the domain, of course, the denominator is always positive. Never 0, because that's outside the domain totally. So we have x half equals 1, x is 2. So the critical point is x is 2. Critical point or stationary point. Now to consider the values. Okay. slightly skewed. So we know that from 1, the function is only defined starting from x is 1. So this part is not considered at all. Then x is 2 is the critical point, and the interval is from 1.5 to 4. Scale doesn't matter really. The scale doesn't matter. The distance between points, in this case in the diagram, doesn't matter. What matters is the correct order. So we are interested in these 3 points. Our critical point, and of course the endpoints of that segment. And what we have to do, all that we have to do is now determine the values of the function and try to, yes, we have to try to simplify somehow. I see that function at 2 is the square root of 4 over 1. That's the value. Square root of 4, that's simply 2. If I have 4, f of 4 would be square root of 16 divided by 4 minus 1 is 3. So that would be 4 divided by square root 3, or that would be 4 square root 3 divided by 3. And finally, the one that I don't particularly like, but I tried to avoid it, postpone it. I couldn't. I have to do it. F of 1.5. So that would be this. I don't need a square root. I can use this form, in fact. I can use this form, which I will do. So that my square root is not so big, not so complicated. So it will be 1.5 divided by the square root of 1.5 minus 1 is 0.5. Now if I multiply by square root of 2, both parts, I have 3 halves square root of 2. So by multiplying by square root of 2, and square root of half times square root of 2 is 1. So this is the correct value. Now, yes, of course, we have to decide which of these is greater and which of these is less. We have to compare now these two values, see? We have to compare these two values. If your calculator, in this course, you may use the calculator. It's only elementary mathematics where you cannot. If your calculator makes it quite obvious, if you see it fairly well, how these two numbers compare, which is greater, which is less, then everything is fine. If the approximate values are very obviously different, if they are not too obviously different, then we have to change, then we have to compare them somehow differently. So 3 square roots of 2 divided by 2 compared to 4 square roots of 3 divided by 3. Let's multiply both sides by 6. So I have 9 roots of 2, or multiply by 6, I have 8 roots of 3. Now I can bring these numbers inside. I have square root of 9 squared is 81, so we have 162 when we bring this into the radical, and here we have 64 times 3 is 192. So it will be this. So that means also how they compare to the number 2. Another question, how do these numbers compare to 2? So if I want to find the square root, 2 is a square root of 4, if you like, and the square root of 4 is evidently less than those 2 square roots. Okay, but this is times 6. So 6 roots of, okay. It's, you see, without a calculator, it takes some skills dealing with square roots. Now that I have started, I need to compare this, but of course, we could also see it this way. 3 halves, the smaller of these numbers. So this is the smaller of these two numbers. 3/2 is 1.5. A square root of 2 is approximately 1.4. It's very, very clearly greater than 2. So 2 is the least value. So 2 is the least value. I don't have to multiply in order to see this, because then, well, you can multiply, of course. That would be 2.1. But I might not even need to multiply to see this. So the least value is f of 2, which is 2, and the greatest is f of 4 square roots, sorry, f of 4, which is, I will still write in the radical form. Because otherwise, well, otherwise, if you find the approximate value using your calculator, you have to write approximately equal to whatever, approximately equal. So if I write it like this, it's the exact value. If you evaluate it, estimate it using a calculator, then you have, it's approximately something. It's approximately something. Okay. Now, next, let's say subtopic, again dealing with optimization. So, for example, a word problem. So the sum of two numbers is 18. The sum of the first number squared and second number doubled is the least possible. So if I say that one of these numbers is x, then the other number is evidently 18 minus x. Now, the sum of the first number squared plus second number doubled, like this, is the least possible. So we need to minimize it. We need to minimize this. How do we find the least value? How do we find the point, actually, where the value is the least? So the two numbers are, of course, x and 18 minus x, but the rest is use calculus. So let's say the function, we create a function that would be this. Just create a function. So we set up these two numbers in terms of x. One is x, then the other one is 18 minus x. Then we set up that sum that is described in this problem. And we are asked to find, let's say, the situation where this sum, this expression is the least possible, to minimize it. This means that if I put it like a function, I write it down as a function in the function form, then we see that this is a quadratic function, x squared minus 2x plus 36. We need to find the minimum point if it exists. Or actually, we need to find the minimum value perhaps, but basically minimum point. All right, f derivative, 2x minus 2. That is 2 times x minus 1. It seems that x is 1 is a critical point. Now we have to investigate, is it really the minimum point? Because it might be accidentally, it might be the maximum point. We don't know before we investigate. So I'm seeing 1, the derivative. Now I see if x is greater than 1, derivative is positive, if less than negative. So it decreases. And we see that it is indeed the minimum point. So we see that the sum, the least possible expression, will be if x is 1, and the second number, 18 minus x, the second number is evidently 17. So these numbers are 1 and 17. Now this is actually where we can use the second derivative test to determine whether this is a minimum or maximum. This is one situation where this would be really convenient. Let me just introduce the idea. We will return to it a little bit later. The second derivative of this function, is if I take the first derivative, this part, and if I differentiate it, the second derivative is 2 for all values of x. doesn't matter what x is. Second derivative is just 2. That means the second derivative is positive. Now we have to know what's going on with the second derivative. Basically, if the second derivative is positive, we have minimum. If the second derivative is negative, at that point we have a maximum. Again, a little bit later, you will see why. But because the second derivative is positive at this point, we have a minimum point. So we can check for minimum maximum in 2 different ways. One way is investigating the signs of the first derivative. Another way is investigating the point using second derivative. Why is that? In a little while. Another problem, optimization problem. A farmer has some 120 meters of fence, and he wants to enclose some area somewhere, maybe for sheep, maybe for someone else, maybe for something else. So he wants to build a fence around the rectangular area, but he wants this area to be as large as possible. For example, he wants a space for his, let's say, sheep or goats, and well, he wants it to be as large as possible, the area, so that they have space. Now, what should the dimensions of the rectangle be to have this rectangle as large as possible area-wise? Because you see, if the rectangle is very narrow and long with the same amount of fence, same length of fence, the area is not so big. And if, well, evidently, if it's too, let's say, vertically stretched out, again, the same thing. You can have the area, you have no idea. Maybe it's not so big, or maybe it's an illusion. Maybe it looks as if not so big, but the length compensates for the narrow width. So let's do it. Let's see. Let's choose one side equal to x. Then the other side of the rectangle is half perimeter. Let's see, half perimeter, 60 minus x. And this is 60 minus x. So if one of the sides of the rectangle is x, the other side is 60 minus x. Now the area depending on x. The area depending on x is width times length. Width times length, which is of course 60x minus x squared. Now we need to find where does this area function have a maximum, because we want to have it as large as possible. So this needs to be maximized. To maximize, to find the greatest possible situation, greatest possible area. So, all right, let's differentiate. So that's 60 minus 2x, or 2 times 30 minus x. We see that, of course, there are some limitations. X, for example, of course, it has to be positive, because otherwise we don't have an enclosure, we don't have an area. And of course, x has to be less than 60, because otherwise we won't have this other side. So this side also needs to be positive. So it has to be less than 60. So x has some limitations between 0 and 60. We see the critical point. Critical point is 30. Critical point, so we find 30. Now let's see again. If x is too large, then the derivative is negative. If too small, then positive. We see that, yes, this is the maximum. This is the maximum point. In other words, the function, so this was the derivative and this was the function itself. The function itself is maximum at maximum if x is 30. 30 is the maximum point. 30 is the maximum point of this function, which means if x is 30, then 60 minus x is also 30. So the conclusion is he must enclose a circle, not a sorry, a square, where all the four sides are equal, 30, 30, 30, 30. So all sides are equal, so it would be a square, and the side is 30 meters. In that case, he will have 900 square meters area. So whatever other rectangle he chooses with the same fence, their area would be smaller. So in this way, we can actually deal with situations. We can deal with situations using calculus, situations of optimization. Another possibility would be, I will not do this to the end. One side of rectangle is the riverbank. So he wants to save the material, not to have to enclose the bank side. So he does it like this. So the river is there. He doesn't need the fence on the riverbank. He has this enclosure like this. In this case, again, we would say, okay, let's say this is x, this is x. So the length is the same farmer. So the same fence, 120 minus 2x. And then the area would be x times this. And we do it exactly in the same way. The continuation goes in the same way. So what we need to solve this kind of problem is to have, let's say, a good idea, a clear diagram. We need a diagram of the situation, especially if it's a geometrical situation. Decide the variable, which will be the independent variable. How can we express all the other things mentioned in the problem? What needs to be maximized? What needs to be minimized, perhaps? That's called optimization. And then just proceed with calculus, with derivatives. Another situation, so I'm leaving this, and another situation, a rectangle, 25 centimeters, 40 centimeters, and somebody, perhaps when you were little kids at school, you made maybe some boxes by cutting out squares in the corners and then folding up. See, you can fold up. You can fold up the sides to make a box or a rectangular dish or whatever you want to make. So like a box. So the question is again, if we have a piece of paper or of tin plate or of cardboard, what size squares should be cut out at the corners? How do we know to get the maximum volume for this? So then we would see, okay, let's say x is evidently the side of each square. That means the width would be 25 minus 2x. That would be the width. Then the length would be 40, again minus 2x, 1, 2. This is 40 minus 2x. And the height of the box will be evidently x, because these are the sides folded up. And then when you multiply all these three for the volume, you have a function that you can maximize. You can find the maximum value. So the volume function would be dependent on x. So if you cut out x, then the length of this box will be 40 minus 2x. The width of this box would be 25 minus 2x. Then what is necessary, what you need to do is simplify and find the maximum point. And of course, there's also this x has to be, of course, positive, and we cannot cut off more than half of the shortest side, of course. So it has to be less than 25 divided by 2, because otherwise nothing remains. Okay. And so basically, these are the conditions. This is the situation that can be solved. Of course, you simplify this, then you find the derivative. You also look at the possible domain. You find the maximum point. In fact, you would have 2 critical points because it's a cubic function. The derivative is a quadratic function, and you would have 2 critical points. Only one of them is good. Only one of them is good, and you have to decide about this. So I am leaving it again to move on. So this is something that you can finish solving, but generally the most typical optimization problems have a geometrical nature. However, there are other situations that are not necessarily dealing with shapes, rectangles, whatever other shapes. All right. Also, like looking at this thing where we got the square, the first of the 3 of my examples here, or the second actually, a square therefore is the most efficient of rectangles, or actually even of quadrilaterals. If you have a set perimeter, then the maximum area is that of a square. Or if you have a set area and you want to choose the shape, the rectangle, then the least perimeter, the least fencing material is again for a square. And this is also when we use methods similar to this, we can in fact demonstrate that, for example, the honeycomb of bees has the most efficient shape, this hexagonal shape, and also a little bit of a pyramid at the top as the lid. So basically, we might even say the bees know what they are doing, because they are creating their honeycomb in the shape that requires the least amount of wax. That can be demonstrated. But now, second derivative and its uses. Second derivative and its uses. Okay. So we have, let me see, 20 minutes for that. Okay. All right. So first of all, concavity up and down, concave up, concave down. So we call a graph, a curve, concave up if it looks like this. So the cavity, as you understand, cavity goes upwards. This kind of curving, when the ends curl upwards, is called concave up. Concave up. Or also sometimes it's called convex. So concave up or convex. If, well, mathematical definition would be if it lies above all the tangent lines on this segment. So if any tangent line on the segment, which we draw at the segment, is below the curve, we say the curve is concave up. Concave up. We use tangents because this approach, let's say in academic mathematics, is the easiest, the simplest way to demonstrate how it links to the derivatives. Now, concave down, also called simply concave, because you can imagine there's a cave, the mouth of the cave. So concave down, the cavity is downwards, or like an entrance of a cave. And we can see that in this case, all the tangent lines would be above the curve. So we call the curve concave down if this curve lies below all the tangents, or simply concave. So you have 2 options. You can talk about concave up, concave down, which is easier. You don't have to think. Or you can call them simply convex and concave. don't mix these up. So either write concave up, concave down always, or convex and concave. Concave can be memorized or remembered by the fact that it really does look like a cave. If the curling, the curve curls, sort of, is curving, ends down. So this is about not the direction, because we can have, as you can see, you can have a function that is increasing and concave down. It could be decreasing and concave down. It doesn't have to have a maximum. Although sometimes, of course, we see that if we have a stationary point and it's a maximum, then the graph should be concave down. Otherwise, it's not possible. Yes, of course. But in principle, you don't have to reach minimum or maximum. It could be concave up. Then at some point, it suddenly becomes concave down. And that kind of point, already familiar from the horizontal type, is called an inflection point. In other words, an inflection point is the point that separates segments that are concave down and concave up. So the inflection could be horizontal, a stationary point, but it could also be, let's say, like this, not necessarily stationary. The tangent line does not have to be horizontal. It could even be vertical. So for example, like this and this. So again, an inflection point that is basically vertical. That means the second order derivative is undefined at this point, and the first order derivative is also undefined at that point. It's also possible. So concave up, concave down, and point of inflection is the point where the direction of concavity changes. If the direction of the concavity changes at some point, this means that's an inflection point. So you can write it with an X, as I did, as I put it in the title, or you can write it with a CT. It doesn't really matter because I've seen both types in textbooks, so different countries might choose different spelling for this. Both are correct. Both are correct. You may write inflection with an X or inflection with a CT. Now let's see, how does that connect to the second order derivative? So let's see. First of all, remember that the first derivative, if the first derivative is positive, the function is increasing. So let's see, if the function is increasing and concave down, what happens to the first derivative? Slope. What does the slope do? The slope decreases, becomes less and less and less. The slope decreases. So the first derivative decreases. So suppose we have a function. So now the first derivative is the slope. And we see that actually if the slope decreases, that means the second order derivative should be negative. Because if the slope decreases, a function decreases, then its derivative is negative. So in principle, we say if the second, I started with a positive first. Okay, let's have a look at the positive. Let's say like this. So we see that if, on the other hand, the first derivative increases, if this function is increasing, that means the second order derivative must be greater than 0. So we see how that second order derivative actually works with the concavity up or down, with the shape of the graph. So the first derivative tells you whether the function increases or decreases, the general direction of the graph, going up or down, or horizontal. Second order derivative tells you the shape of the graph. Is it concave up or is it concave down? And so we see that if the second order derivative is positive on some segment, then the function is, the graph is concave up. we can also see that this is also true if the function is decreasing. If the function is decreasing, then second order derivative positive still means concave up. So the general shape of graph is concave up. If, on the other hand, the second order derivative is negative on some segment, then the function is, as we saw in this case, concave down. Then we have function concave down. If the second order derivative is zero, if the second order derivative is zero, then it doesn't mean necessarily, it might not be an inflection point. What this means is that if second order derivative is zero, we need to see what the signs of the second derivative are on both sides. Is it an inflection point? So if the signs are opposite on both sides of the point where the second derivative is zero, then we have an inflection point. If they are the same, then no. Then it's simply a point where the curving actually continues. All right, so how to remember this? You could think concave up, second order derivative is positive, so we can add water to the dish. Second derivative negative, the water is spilling out of that dish. Concave down, if we turn the dish upside down, right? So you can remember it like this. Another possibility, positive feelings, happy function, negative feelings, second order derivative, unhappy function, concave down. Concave up, like smiling, and concave down, sad, depends on the sign of second order derivative. Positive, happy, negative, unhappy. So these are the ways by which you can memorize for the sake of investigation, so that you don't have to remember the formula, but you can simply say, okay, in this case, it's positive, it's negative, concave up, concave down, whatever is necessary. Some examples. How do we use second order derivative to investigate the shape of the function? So the first derivative, 3x squared minus 4x minus 4. Second derivative, 6x minus 4. Okay, so for the first derivative, the critical points, if you actually decide to factorize it, or you decide perhaps to use the formula to find the critical points, to find the zeros of the first derivative, they are 2 and minus something, minus 2/3. And we see that for large x values, this would be positive. We can factorize it. In fact, of course, we can say 3x plus 2 times x minus 2. If you factorize this, I am skipping that part. I am doing things very quickly because this is an algebra skill. For that, you had elementary mathematics for doing this. And now we see if x is large positive, then both factors are positive and the derivative is positive. If x is between minus 2/3 and 2, for example, 0, we see positive times negative, it will be negative. And if x is, let's say, large negative value, both factors are negative, product positive. So the function is increasing, decreasing, increasing. Then for this, we see that second order derivative is 0 if x is positive 2/3. Now, if I do a second sign diagram so that my positive 2/3 falls between negative 2/3 and 2, so that the points fit on both lines. So on two levels, but the numbers fit. Now, the second order derivative is evidently if x is greater than 2/3, then the second order derivative is positive, if less than negative, which means the function is concave down And here the function is concave up. And now you see what happens. You can understand what the graph might look like. I am not determining the other coordinates of the points on the graph, but you can understand that the function is increasing concave up, reaches maximum at minus 2/3, or I will draw here, increasing concave up, reaches maximum at this point, 2/3, starts going down, is still concave down. Still concave down. Now at 2/3 inflection, it becomes concave up. It becomes concave up at this point. Still goes down, reaches minimum at 2, and then starts going up, still staying concave up. In other words, we have minimum point and maximum point, and we have inflection point, and understanding what these points mean, especially inflection, tells us, it gives us information about the shape of the graph. It's the shape of the graph that we see here. I don't know the exact coordinates of these points. In other words, that is, I don't know the y coordinates. I do know the x coordinates. This is at x minus 2/3, this is at x plus 2/3, and this is at x equals 2. I simply don't know the height, I don't know the y values, but the shape is pretty clear now. Now we understand what the shape, the general shape of this function is. Okay. What is very interesting that at some moment there were 43 of you, and in the chat there are 43 of you, and now there's only 35 remaining, 36. All right. I will now do something. So sorry about the delay because this is a really annoying thing. Okay, some people have unstable connection, but basically I would ask you to write your names again. Just write your names again while I'm going on. Okay, I need to make sure who is here, because this is getting really annoying. If somebody shows up for 15 minutes, obviously not you here, but if somebody shows up for 15 minutes and then starts telling me that, no, I don't study by your lectures, I study by something else, that's something that is not acceptable. Okay, now, again, just to find the inflection points, here at this moment. Let's see, okay. The first derivative is 4x cubed minus 12x squared plus 9, what? 36 plus 36x squared plus 96x differentiation. Second derivative, 12x squared minus 72x plus 96. I'm taking 12 out of parentheses. X squared minus 6x plus 8. So we see the two critical points of second derivative. Again, we do the sign diagram and sketch the whole thing. First derivative is 0 if x is 4 or 2. Second derivative is 0 if x is 4 or 2. We see that if x is greater than 4, for example, 10, we see this is positive, the derivative, second derivative. If x is between 2 and 4, for example, 3, we have 9 plus 8 is 17 minus 18 minus 1 negative. And if x is less than 2, for instance, 1, we see it's positive again. So the function is concave up, concave down, concave up. So I have two inflection points. I have one inflection point at 2, and I can actually put in the value of x into the function and find it. And the other inflection point at 4, again, some other function value. At this moment, again, I'm just trying to save us some time. because time is rather short. We only have 2 more lectures in this unit next week, and then there's the unit test on Friday, next Friday, if you remember. But again, this is something that you can already start doing for your homework. You can investigate the concavity up or down of your functions. Also, please note, if the direction of concavity does not change somewhere, for example, if you have plus, you have this critical point where the second derivative is 0, you have plus, and then another point perhaps where you have negative afterwards. So the whole idea is concavity doesn't change. So this is no inflection because it doesn't change the direction of curling. If it curls up and then afterwards it still goes on curling up, even though at that point it became rather flat. 0 second derivative simply means a certain kind of flatness of the graph. The graph is quite flat at that point, but that's all. It could still go on curling up. And the only inflection point is where the direction of the concavity changes. And finally, I would like to consider this second derivative test for finding extremum points, for checking extremum points. Second derivative test. So what we did so far for maximum minimum points, okay, here we also have the properties. I will go back to that later. But to determine the extremum points, we find the first derivative. In this case, it would be 3x squared minus 12. That is 3 times x squared minus 4. So we understand that this is 3 times x minus 2 times x plus 2. Which means that we have 2 critical points. X1 is 2 and x2 is negative 2, 2 stationary points. So this means that the tangent line at these 2 points is horizontal. Now, the general idea, what use would be the second derivative test for extremum points. And that is this: if the tangent line is horizontal and the second derivative is negative, so the function is concave down, then at this point, if the second derivative is negative, at this point, it is stationary because the first derivative is 0, and it's concave down because the second derivative is 0. You see that this must be a maximum point. This must be the maximum point. So basically, we have the rule approximately like this. If the first derivative at some point C is 0, so it is a stationary point, and the second derivative at that point, we don't find inflection points. We simply determine what happens to the second derivative at this point. If it is negative, then C is a maximum point. C is a maximum point. On the other hand, if we see that at some point of the graph, the tangent line is still horizontal, but the second order derivative is positive, the graph is concave up, we understand that this must be a minimum point. There's no other possibility. So if the second order derivative in such point is positive, then that means that C is a minimum point. What is bad? If second order derivative is 0 at C, then this test doesn't work. Then we don't get information. So this test, the question remains open. The question remains open. This test only gives us an answer when we check stationary points if at the stationary point the second derivative is positive or negative. If it is 0, then it could be anything. For example, if we consider the function y equals x to the fourth power, then we know that if x is 0, the first derivative is 0, the second derivative is 0, and we have a minimum point. If I have a function y equals minus x to the fourth, x to the fourth, or square would work exactly that, just as well. Again, if x is 0, the first derivative, okay, for x cubed is 0 at 0 point. So it is a critical stationary point. The second order derivative, 12x squared, is also 0, but because this is minus x to the fourth, it has to be a maximum point. And if we consider the function x cubed, then again, both first and second derivative are zeros when x is 0, but it is an inflection point. It's neither minimum nor maximum. So we see how with this, we cannot answer that question. So if we see that the second order derivative is also 0, it simply means that we have to use another method. We have to check the signs of the first derivative. In some cases, finding the second derivative is easier than checking the signs. In other cases, checking the signs is easier than doing the second derivative test. So it's up to your discretion, up to your understanding which manner of determining the extremum points, establishing maximum minimum points is more convenient for which function. That happens after you find that first derivative. So in this case, if I see the first derivative, if I want, I could actually investigate the signs for this. But in a way, it's actually faster to do the second order derivative very quickly. And let's do it now. So the second derivative of this function, is 6x. So this means if x is positive, second derivative is positive, that is, function is concave up. So this means f second derivative at 2 is positive and the function is concave up. So this means 2 is a minimum point. So x is 2 is a minimum point. And the second derivative at minus 2, is less than 0, negative, because it's minus 12, right? So this means that x is minus 2 is a maximum point. This is all very well if this is easier than looking at the signs, than the sign diagram. So we may use sign diagram, or very carefully we can use the second order derivative, the second derivative test, to establish what situation do we have. All right, so we have to finish now. So at, let's say 4:30, let's give you a break. Grab a coffee, tea, water, snack, whatever. I know that there are 4 people, 2 who need to write the first elementary mathematics test, and 2 who need to write the second elementary mathematics test. So at the moment, I will not close the link, so you will be able to come back at any time you like. So at 4:30, that is in 25 minutes, let's come back. So I will be here, and basically 4 of you are expected here back, so that you can write the first or the second unit elementary mathematics test, whichever you need. So I will switch off everything and stop the screen share, but I will keep the Zoom link open.